So, ladies and gentlemen, tonight will be my last presentation, number 7, by the way, on energy medicine. And the reason why I have Karnak the Magnificent up there, it's Johnny Carson, is it became kind of just a running joke, basically a automated response at the end of his stack of letters. So what he did is, in the envelope, he had the answer, and he'd read the answer and then pose what the question was. And most of the things were so ridiculous and sometimes not funny that it became a running joke that he'd hold up the last envelope, Dr. Harshfield, and say, and here I hold the last envelope. And before he even opened it, the audience would break into this huge cheer, because they were sick and tired of all the envelopes he went through. So my inference here is you're probably sick and tired of hearing the energy medicine topic. I am definitely not as funny as Johnny Carson, I can tell. But did I nail it, Dr. Harshfield? Do you remember that explicitly?
Absolutely. Ed McMahon would sort of help kind of lead that as well.
I don't want to say you look like him, but maybe between the two of us, there's a little congruency there.
Here's Tommy.
Good for you. So anyway, this is our last session on energy medicine, and I hopefully I improved it from Monday, and we have a couple slides at the end. And as I click my button here, let's find out how we get down. Excellent. And because we talked about the last time I talked was about hyperthermia. I was listening on a long journey over the last week to Andrew Huberman, who's a molecular biologist or neurobiologist and ophthalmologist, but he runs a really good podcast, and they're always long. Like you can see, this one's 2 hours and 41 minutes and 37 seconds. But he's very thorough. And Rhonda Patrick, of course, is a cellular biologist and very intelligent lady, and found my fitness, and she's really, really big on sauna. And so I think to augment what I talked about on hyperthermia, you can go to, say, 1 hour and 50, and there's a link to it, and talk about, sort of an augmentation to just hyperthermia with hypothermia and what that does. And what I didn't mention it on Monday, but what Huberman talked about is, he has a lot of hormone people on, and they show that if you do 30-minute hyperthermia events, maybe with a hypothermia in between, it raises human growth factor by a large number. He said like 9 times. Those numbers aren't credible, but it raises it substantially. But what I also liked about that talk, and sort of the end of it, is both Huberman and Patrick, really brilliant people. Huberman's a professor at Stanford. And if anybody knows about Cynthia Kenyon and her work on nematodes, brilliant Nobel Prize kind of work. But they admitted their own foibles, where they fall short. And like Huberman doesn't like fish, and Rhonda Patrick doesn't do weight-bearing exercise. And so they were all kind of like being very honest about their level of compliance with their own flaws. So I thought that's just an interesting point to bring up. Wayne, your trouble. It's just an interesting point to bring up. And Huberman said something I've been saying. If you can be 80% compliant, you don't have to be 100% all the time. I know people like myself who eat a lot of ice cream and cookies now and again, but they're relatively compliant the rest of the time, and you can get away with that, particularly if you exercise. And that's the key thing: burn off those calories, whatever. But really good talk. What Rhonda Patrick doesn't present anything unless there's many studies corroborating it. And the real study she has on sauna is from Finland, and they don't compare people at a lower latitude. So it's kind of like saying, I'm going to study vitamin D at latitude 45, not at the equator. So you don't have a full spectrum of data. So there's always, there's there's always trouble with studies, so we can't take every piece of information from every study as absolute gospel. We've got to look at the, all the multifactorial aspects that need to be considered in human physiology. And, I love Thomas Sowell because he talks about, differences in people. And he talked about the Niger River versus the Mississippi and how that affects cultures in the United States versus Africa. The Niger River is impossible to navigate very far, whereas the Mississippi, very quiet river, very easy to navigate. So people living on the borders of those two rivers are economically very different because of trade variations. I don't know why I brought that up, but just there's a lot of subtleties that we tend to ignore. So when we look at a piece of data as gospel, it's not always that way. We need to look at it. And then Huberman, to his credit, understands the difference between conduction versus absorption. He didn't use quite those terms, but see, saunas heat by conduction. So you heat the outer layer of your skin from the outside because of the warmth of the sauna room, 174, I think she was talking about degrees Fahrenheit, pretty hot, or 169, something like that. Then it will conduct through your body, so you have to stay in it a long time. Whereas the infrared light, coupled to the thermal heat of conduction, will warm through absorption. And absorption is going to heat you up much more quickly and efficiently, assuming that the light you're using can penetrate fairly deeply. And a lot of the infrared light will penetrate, not just, and Huberman said, well, it'll go down a couple layers of the skin. No, it goes down much deeper than that. It can go down much deeper. And hopefully you now know that when infrared light goes down, and when it does finally reach something, a molecule of substance that can interact with it, it warms that molecule up. Not much different than a microwave heating your food. We all say it heats from the inside out. It doesn't. It heats through the whole, wherever there's water, it's heating it, but it's heating it throughout the entire cross section of that material. So that's why I think the infrared saunas, you want one that has light as well as heat, heat from conduction. But if you stay in it long enough, the whole idea is they're talking about the temperature inside the sauna. The only real temperature that matters is the temperature inside your body, your core temperature. And then we had this discussion on Monday about everybody should get themselves a mercury thermometer, so we actually have a standard to really measure very accurately what your core temperature is. So anyway, without further ado, I mean, that was, just sort of rehashing and supporting the last discussion on hypothermia. But I think hypothermia, I did this race, 1994, and we had as they say in Boston, a wicked hot tub in our condo, and then we had an ice bath, and we were just cycling between the two. And so even 20 years ago, we recognized the benefit of vasodilation and vasoconstriction as sort of a process to improve blood flow. So they work symbiotically to an extent. Rhonda Patrick says she talked all about going into cold, and she said 30-second immersion at a certain temperature. I think it was like 49 or 59 degrees Fahrenheit. And it's a miserable experience. And she sings out loud for the whole time so she can endure it. But now, living on a lake, I'm thinking of going in the lake tomorrow morning, but I probably won't. We got to find other means to get the cold therapy. So, in order for something to happen, if we're chemical reactors, how do we know? We have a body temperature above the ambient temperature, we hope.
Right, how do I turn it up?
And so we know chemical reactions are happening. And when chemical reactions happen, there's either a transfer or sharing of electrons. That is the most fundamental thing. It's donating or accepting electrons. So and we talk about it, we talk about oxidative stress, right? So oxidative stress means loss of electrons, most fundamentally. And then healing is a gain of electrons. And, Tom Levy talks about that. That's my final slide, not this one. No cheers, please, yet. I'm not done. But this fundamentally is what it's all about. And, but also, so electron donors include sunlight, electricity, food nutrients to affect chemical reactions, because you need to have energy to push things uphill to produce those electrons. So obviously we have to have food. And electron stealers include infections, heavy metals, toxic substances, highly oxidized substances, inflammatory oil, foods, seed oils, things like that. And then there are other things that share electrons. Not everything just like one grabs the electron from something else. But to move electrons around, you kind of have to have this upper process as opposed to sharing. But most things share. Most things aren't quite so greedy. They do share in physiology, but they're not really fundamental to a lot of what goes on in our physiology. So this is a new picture, and I'm just this was some halftime show or for the Detroit Pistons, and they were challenging people to stuff a basketball, and this gal here didn't quite make it. And my point is here, the reason why some things don't work is we don't have enough oomph to get over that hump. Now, this is why I don't like my, let's see if I can go page up. Amazing. So like, if you don't have enough oomph, this reaction may not occur. And if this is a healing reaction by giving electrons, it's not going to happen. So that's why some pharmaceuticals, some interventions, some supplements, some energy medicine doesn't work. It doesn't quite have enough oomph. So that's the electromotive potential. And if you folks remember that term, I remember when I was doing 3rd, 4th, 5th grade science shows, and I was trying to get them to remember the term sublimation. And with the electron recycler, Andrew, I'm trying to get him to remember. What term am I trying to get you to remember, Andrew? Let's see if he gets it. Oh, I'll answer it for you, Andrew. Stoichiometry, but that's another whole thing. But so electromotive potential. See, so if it's all about electrons, that electron has to have enough oomph. It's like, does a 1.5 volt battery have the same oomph as a 9 volt battery, or as your 12 volt battery in your car, or the electrical circuit, the electrical outlet in your 220 volts? So everything has sort of a different level of oomph. That's why things may work or may not work. When this gal didn't dunk the basketball, she got 0 points. She did land on a 1 foot thick mat, so she was fine, but she still didn't score. And if we're trying to change something in our physiology, but we don't have enough height or oomph to do it, it's not going to work. So, I mean, I think it's important to understand why things work, but also why things don't work. And it's actually thinking about this, and I appreciate you, Dr. Carter, for making me write this book. It's sort of changing my philosophy in certain areas of how I recommend treatments, for example, because we never quite know. So therefore, if we keep doing the same thing over and over again and it's not working, it doesn't mean the mechanism is wrong. It doesn't mean it couldn't work in other circumstances, but what it really means is that particular treatment just doesn't have enough oomph to get up and stuff the basketball in over the rim. Michael, you're agreeing with me. It must be, I must be on to something.
Absolutely.
So all reactions involve sharing of electrons, like I showed the bottom picture, or donating and taking electrons. And then there's this in-between state, like, for example, water.
Hello.
We'll have to say goodbye. But like water, hydrogen and oxygen, even though the electrons are shared, the oxygen holds most of the electrons, or at least probabilistically in quantum physics and chemistry, the electron's spending a lot more time on the oxygen than on the hydrogen. So the hydrogen has what we call a partial positive charge, and the oxygen has a partial negative charge. And then the oxygen will then interact with another water molecule at the hydrogen so that the plus and minus attract. And that's what makes water stick together so well, particularly at the interface, and create what we call structured water. But I have the story I told on Monday that there I am at Snowbird and taking a little shuttle bus for 4 minutes from the bottom of the lift to my lodge. And some guy was admiring the fact that I wasn't wearing ski goggles, the only one on the mountain that wasn't. And he wanted to know what they were. And then we just started chatting. And he's an IT sales engineer, but doing sales. And he asked me what I was doing. And then in the scant 3 minutes I had left, I explained how the basis of IT, information technology, and the basis of human physiology are identical. Okay. And just the reason why I'm bringing this up is, nature is, there are only some fundamental things that go on in nature. And in our physiology, anywhere in the world, it's this, anywhere in the universe, this is what's happening for the most part. So, a computer uses combinations of zeros and one to carry out all processing. Your body is similar that it uses electron donors and electron acceptors. So electron donor could be the 1, electron acceptor, the 0. I'm not exactly sure how the 0 and 1 terms work, but they are definitely related. So oxidation is when a substance loses an electron. Reduction or anti-oxidation is when a substance gains an electron, so the electron acceptor. Now in integrated circuits that make your phone work, make the computer work, make everything we have in communication work, transistors at the base of everything, we have different types of semiconductors, an N-type and a P-type. And these are the primary materials. So what happens is silicon, like carbon, is relatively neutral. Okay, it's somewhat happy because it has 4, I won't get into that too much, but we have what are called doping materials, and some are kind of devoid in electrons by 1, and some are rich in electrons by 1. Donator, acceptor. Okay, and I think I have this explained now, except I don't know how to hit the button. There we go. So I'm just repeating this. So a P-type semiconductor or electron stealers, they have a little hole, and they want the electron to fill that hole with an electron to kind of round things out, make everything sort of neutral, if you will. And N-types are donors. Well, we don't really need to know that, but I'm just sort of showing you that healing is Tom Levy, healing is donating electrons. Degeneration is stealing of electrons. It's the exact same process. So now I think I have a little explanation of it here, and I won't really show you what this is all about, but boron wants an electron. Astatine wants to give an electron. Okay, and in P-type, but this is why this is the key thing. Silicon, the material of semiconductors, is relatively stable. It's not a conductor, or if it is, it's a very poor conductor. It's much more of an insulator. But you add an electron donor, astatine, or add an electron stealer, and you completely change the nature of the silicon so that electrons can flow. Now it semiconducts, aka communicates. Capiche? I mean, obviously we're communicating, right? We have little semiconductors at the root of everything that's making this happen. But it's just electron donors and electron stealers. It's same as in health. The core of health is electron stealing and electron donating. So all reactions involved, we're going to have to talk about that. Another purpose of redox reaction. So this is a redox reaction is, one steals, one donates. That's a redox, oxidation reduction reaction. Another purpose of redox reactions in living body is cellular communication. So what do our chips do? Redox. And what do we gain from this? Ways to create electricity for communication in a very specific way. So let's see. Metabolism alters redox reactants both rapidly and transiently. So we have acute disease and chronic disease, as well as in various long-term steady states. Okay. Redox reactants comprise an energy-sensitive communication system with each cell within the cellular compartment. So in other words, it's highly tuned. It's highly tuned. And the reason why in semiconductors they use gold leads is it's not going to corrode. What does corrosion do? It breaks up those energy sensitive communications with something that's resistant. When copper or aluminum corrodes, you get an insulator, it doesn't communicate well. Well, guess what? In your body, oxidation can do the exact same thing and basically compromise or reduce the communication because you don't have this energy sensitive communication system on the cell. And we'll talk about that in a minute. So variations in a metabolic state impacts the response of tissue to other communication. Metabolic, it really should be inflammatory, oxidative. Those are really the right term, not necessarily metabolic, but who am I to contradict Corky? Well, his name is Corky, so I got to contradict them. But anyway, so energy medicine and molecular and cellular communication, how do molecules and cells communicate? I'm just going to read it. I don't have it memorized. If you have an infection, how does your body know about it and send substances to kill it? Kill the infection and control the inflammation. Okay, so there's a break in the communication. And it's like, you know, the Indians are sending smoke signals and a big wind comes and blows it away. And then you realize there's a problem with the communication and you go and try to solve that. Not a very good analogy, but you kind of get what I'm getting. So fibrinogen is a signal molecule. It recruits fibrin to go and stitch a wound. How does fibrinogen get its signal and pass it along to ensure fibrin is notified? Okay. Electromagnetic, I wonder if I wrote that. I can't remember, but that looks like something I would have written. But electromagnetic interactions is the emerging model for how communication occurs within biological systems. And this is Dr. Harshfield, my credit to him. And he reminded me about this. When something can vibrate in the vicinity of a receptor, it creates co-resonance in the molecule receiving the signal. That is what turns it on to perform a response of some type. Think about a tuning fork, a specific design that puts out a narrow frequency. David, you want to come in and explain your the tuning fork lesson you taught me a few months ago?
Well, it has to do with resonance imaging, which kind of the most complicated form of that would be the MRI machine, magnetic resonance imaging, using the Larmor frequency of these precessing molecules. And we learn exactly what the frequency of rotation of hydrogen is, and that's how you produce pictures in an MRI field. 99% of the molecules, I think, are hydrogen because they're so small. But what we try to do when we're trying to make hydrogen make pictures is to find exactly the frequency it's precessing. It's like a wobbly top, a top spinning and it stands straight up. Then it starts to kind of lay over and then it kind of precesses. That frequency is very specific for hydrogen. We're made of hydrogen, so we can use it to make pictures. And what we do is we send in a resonant frequency identical to the precessional frequency, and they vibrate together. And now the amplitude, it's the same frequency, but a larger power amplitude. And like we talked about guitars, I know Andrew's got a little Les Paul behind him. If you pluck the A string on that guitar, it's 432 hertz. And the guitar across the room or in the next room, its A string will also vibrate, not the E, D, G, or B strings. So the resonance is very specific, and that's why the pulse EMF is so important, that when your liver resonates at a certain frequency, to make it healthy, we need to put the same frequency in to vibrate at a higher magnitude. Back to our MR example, by putting this frequency into hydrogen, it makes the precession lay down more. and it sends the signal out as the hydrogen is laying horizontally. It's like a lighthouse. Every time it comes around, it goes blip.
So
Blip.
David, with PEMF, if we knew the frequency of the tissue we wanted to heal, we could run that specific frequency, but since we don't, we run a broad spectrum of frequencies, correct?
And I think the reason that Dr. Tennant does that is that if you know the liver, let's say, vibrates at 490 hertz, and I want to get 490 hertz of pulsed EMF into the liver. Well, by the time it goes through the skin, in the subcutaneous fat, in the capsule, it might be 450 hertz. It's not the right frequency. So to your point, he uses a broad bandwidth,
There you go.
like 550
Or,
to
or we might have
350.
lost intensity as well.
Yeah. And so when some of the higher frequency energy goes through the skin and breaks down to a lower frequency, at some point in time, there will be an energy that is exactly the right frequency to stimulate that liver. And what's cool is whatever is out of frequency just goes right by. It doesn't hurt anything.
Correct. And, we're more to the fact of changing the subject just slightly, but this is still redox, is what's going on at a cellular level. And we spend a third of our energy at least just pushing things into and out of cells. That's an energetic process. It takes energy to do that. So that's why you have a baseline core temperature. There's a lot of energy expended to make that process work. It's an energy robbing system. So it takes a lot of energy production to create that. So on the top, I have a lead acid battery. And basically you have the lead, which is charge 0, and you have the lead oxide, which is charge 4. And there's a flow. And I have a little thing over here, and so you get a flow of current from lead that has a lot of electrons to a lead +4, which is devoid of electrons, and you get a flow of electrons in that direction. And then you get the lead oxide or lead sulfate in solution. So your alternator is actually an antioxidant, because when your car is starting, you got a big load going this way. And then when your car gets running, you put some energy in the alternator and it pushes it in the other direction. And the reason why your battery eventually fails is because you get some of this lead sulfate that precipitates, and you start losing this. But that's not relevant. I mean, that's aging. That's aging of a battery, I guess. But see, this diagram is meant to show that the same thing's happening sort of at the cellular level. You have a little battery here where you have charges, a net negative charge inside and a net positive charge on the outside of the membrane. This is the inside of a cell, phospholipid bilayer, and a positive net charge on the outside. And it's really important. And what the authors of this molecular biology paper talked about is many crucial processes in the life of cells depend on active transport. Sodium potassium pump is what they call this thing, but really, how do we make it work? Active transport mechanisms may draw their energy from ATP, light, and the input of electrons. ATP, food, light, sunlight, electrons, and we're producing electrons internally, but that's where some of these energy medicine techniques can contribute to the most crucial processes of the life of cells. Okay, so all of these play an important role: energy medicine, light medicine, energy medicine, and then food. So that's really the foundation. And now I have this sedimentation rate here because basically you have a net positive charge, but what you really have is a flow, because this is a continuous process. And when you have a flow, you have a current, and we create an electromagnetic field, so a magnetic repulsion. Positive charge is going to repel each other. And so the best way we can measure it, and unfortunately, unless we go into some very in-depth, in vitro, maybe out of the body measurements, it's probably very hard to measure this process and see how efficient your process is. But in my opinion, the sed rate is the best marker, because we're literally measuring the charge on this outer membrane, how robust that charge is, because that charge affects repulsion. And repulsion means that red blood cells don't want to stick together, which means when they're being pulled by gravity, they resist the force of gravity because their repulsive force is so strong, it's actually stronger than the pull of gravity, and they'll stay up in solution. That's why I consider the erythrocyte sedimentation rate such an important biomarker. It's not extremely precise, not extremely accurate, but it's really the best we have to measure the electrical potential of the cells of every body, every cell in your body, not just the red blood cell. Because you know, this picture here doesn't say this is just the phospholipid bilayer of a red blood cell. No, this is the phospholipid bilayer of all cells. Okay, so when we measure the red blood cell and its charge, it is reasonable to assume that it's a surrogate for what's going on in all cells. So that's why I love this test. And you know, this graphic is nice because it shows that really the factor driving this or preventing these cells from settling is electricity. And the standard of care numbers are whacked. And this slide I made a few years ago, and now LabCorp says 0 to 40. You want to be 2 or less. 3 is unacceptable because it's not a very precise marker. So when you're at slightly above, you're discharged. You know, you don't want to be working at 80%. You want a fully charged battery. And, you know, this is just showing apparently healthy men, and the green rectangle was when I thought 6 was a decent number. And now I've done enough studies to know that I want you to be 2 or less. So really, where you want to be optimally is here. And you can see most apparently healthy men are suboptimal. And you may say, once again, 3 not bad, but it's really not good. And then the measurements, you know, when you get a LabCorp measurement of 2, I don't think it really means you're 2. It's like the lowest end of detection for a relatively crude test. So I consider 2 to be relatively 0, just based on hundreds to thousands of SED rates that I've evaluated. So a very important test. It all relates to the dynamic of the energy at the cellular level. And if you don't have good cellular transport, then what do you think is going on with the mitochondria buried deep inside the cell? It's not getting its electricity or its nutrients, all of which, because you know, the first line, I published my energy medicine chapter today on my blog if anybody wants to read that. But the first thing I say is, look, we're biological creatures, but the biology is there to just support one thing: electricity. So let's see. And I like this study I found on PLOS. I used to know what it means, but I forgot. But we show that our method of measuring the electrical conductivity credibly reflects the ESR, the erythrocyte sedimentation rate. So let's reverse that. The erythrocyte sedimentation rate credibly reflects electrical conductivity of the cell. Extremely important concept. So the cell membrane, also called the plasma membrane, is found in all cells and separates the interior of the cell from the outside environment. The cell membrane consists of a phospholipid bilayer that is semi-permeable. Once again, they're not saying the red blood cell membrane, they're saying cell membrane. The cell membrane regulates the transport of materials entering and exiting the cell. Some of those materials are charged minerals. Okay, you have a lithium ion battery, you have a lead acid battery. You call it an ion in, you know, the regular world, but in physiology we call it a mineral. Mineral, ion, same thing. So you need good ion transport through the cell membrane to create that charge, to get your SED rate down. There are other factors that can impact the charge, inflammation in your terrain. in your extracellular terrain that can affect the charge in that membrane. But the main thing is this active transport process. If you don't have good active transport, your sed rate's going to go up, and your energy of your batteries, your cells are going to go down. Not a good thing. So that's it for that part on redox. Now the last two things are on microcurrent therapy. I didn't do a lot of research into this, but the highlight is there's TENS and MENS. And Cleveland Clinic says that TENS, which is really the pain energy modality, versus MEMS, which is kind of the healing modality. So TENS works by either stimulates nerve cells that block the transmission of pain signals, or modifying your perception of pain, or raises endorphins or something like that. So I didn't really dive deep into that. So microcurrent stimulation, TENS is a milliamp, whereas the MEMS is a microamp. And so what I really conclude here is TENS is best for pain, but MENS, a higher amperage, is best for healing. And it makes sense because we need electrons to heal, and so we need a greater flux of electrons. And what Dr. Pollack, I think, very astutely pointed out, and I'm not going to go into PEMF because he did such a great job, is that the Faraday effect using PEMF creates electron flow, but the difference between TENS, MENS, and PEMF is that the magnetic field, the magnetic energy, can penetrate unabated deeply into tissue. The only thing that abates it is that the signal diminishes with the square of the distance. That's why you want more Gauss, but it's able to create electrons like TENS or MENS much deeper into the body. And I think that's the key take-home lesson from that. So we're wrapping up actually here. Some extra electrons are needed for healing because as cells are damaged, they become electrically imbalanced. So I had atrial fibrillation 20 years ago, and I believe it was mainly, and there's good data to support this, but in myself, I believe it was due to Lyme disease, electron stealer. So literally, if we have a pathway of electrical conduction between the upper and lower chambers of the heart, and we have an infection, a focal or localized infection somewhere along that pathway, it's stealing electrons and creating an electrical imbalance. And it's kind of like you look at a meandering river. At one point, it was going straight, but over time, it found things that interfered with the straight pathway, so it diverted around it, and then it diverted even further and diverted even further. And that's really all atrial fibrillation is. As a result, the electrical current takes the path of least resistance through the body, and injury inflammation generally means oxidation or a lack of electrons. So atrial fibrillation, chronic pain, all these things, all these signals are related to you're electrically imbalanced due to some inflammatory toxicity, electron stealing process. This process either consumes or diverts some of the body's natural electron producing anti-inflammatory processes. By either mechanism, the body's electrical current will bypass the injury. This is text from a research paper on electrical treatment, MEMS or TEMS. So by either mechanism, the body's electrical current will bypass the injury rather than go through the injured area. And healing the damaged cells and tissues would take time. However, by providing electric current, or for that matter, since this is promoting TENS and MENS, any good source of electrons that can be delivered to that area, light therapy, good nutrition, something anti-inflammatory that breaks that blockade of electrical imbalance, will stimulate healing. Okay, so however, by applying electric current to the site of an injury, supplemental electrons are provided and recovery will be accelerated. It's really good data actually out there on using microcurrents to enhance healing after surgery and things of that nature. So it's not sketchy science whatsoever. I'm not really going to talk about scalar energy, but I think at the end of the day, Tesla, you know, was able to measure it. Einstein acknowledged its existence, but at the end of the day, we see from scalar energy the same impact of electrical or PEMF, things of that nature. And so I think what we do is we're the scalar energy may be what's called a static energy, but at the end of the day, electrons are made available. So repairs DNA, protects cellular DNA from damage, stimulates cell growth in human immune cells, improves cell wall permeability. So that, what is that? That's all about active transport. It's all about charge differentials. So at the end of the day, I think scalar energy is also all about providing electrons as well. And then here's Tom Levy. And the reason why I bring him up is because I was listening to Jonathan Otto, one of Jonathan Otto's talks where Tom Levy was on, and he said, all really astute doctors understand that healing is electron donation, degeneration is electron loss, and then I've added this third one. Treatment is reducing electron stealers or providing electrons, or maybe better yet, both, because maybe providing electrons is a temporary fix, whereas reducing the electron stealers is more of a root cause. And with that, I have no choice but to bring us back to Karnak and Magnificent. So anyway, I love Mike Adams, but I must say the article that came out about ultrasound being the ultimate cure, not so much. But I'll give you some research on this just to answer this, because you know, when you look at energy, anybody know who that guy is up there in the picture? David Harshfield, you know who that is? Did I get you, David? Or did I lose you? I think we lost Dr. Harshfield because I knew he would answer. That's not Nostradamus. And what he said is, after assessment gives a unique frequency to operate in patients, waves of sound kills the cancer. They become lifeless and the poisons leave the body. Well, what does that have to do with electrons? Electron donating, electron stealing. It turns out that yours truly, with 3 other rather scientific guys, developed a molecule for what's called sonophotodynamic therapy. And I had a lot of discussion. One of the guys was not David Dolphin, but someone else who said, I don't believe you can activate a molecule with ultrasound. But there's a physicist that recently retired from NIH, and he was a good dude, very, very bright physicist. And what he showed is that ultrasound can create local hyperthermia, high temperature. But see, when a liquid in your body goes to a gas, it expands by 1,000-fold, okay? Then you create this bubble. And when that bubble implodes, it releases so much energy that it actually can produce light. And what I think is happening with ultrasound is, in this process called cavitation, you actually produce electrons. You know, I showed you many moons ago on energy medicine that our body glows internally. Okay, so we're producing light inside our body, and there's reasons for that, which I explained, I won't get into now. But I don't think ultrasound is fundamental. I think if you had a cohort where you did ultrasound, light therapy, electron donation, electrical therapy, that you'd find the ones that provide the greatest flux of electrons are going to be the ones that outperform. And so that's not just a guess. It's based on, we created this molecule that absorbs light and also is activated by ultrasound. And there's no way a molecule is activated to produce an electron by ultrasound. There's not enough energy. It goes UV, highest energy, visible, infrared, microwaves, sound. Okay, so it's not enough energy to promote an electron or make an electron available. But I believe under certain circumstances, there can be a concentration of that ultrasound energy to then affect either enough heat or a small amount of light to produce available electrons, or maybe the heat alone does that, and then produces that healing effect. Because if I stick to the basic precept that electrons are healing and the removal of electrons is degeneration, then somehow, and I mean, look, that's what your mitochondria do. It's an electron transport chain. Okay, so how do we support that with ultrasound? Somehow it has to go through processes to produce the electron. And with that, so I answered that question, Steve. So, it's never one thing, but, I can, if anybody's really interested in understanding, you better be ready to read something intense, how ultrasound actually can produce a higher energy end product by concentrating heat through this cavitation process. I can send you Dr. Peter Reese, the physicist's research papers on this. Any takers? But yes, I've read that stuff. And let's see here. We have some questions. Let's see. We'll go to the top here. I can't answer that one, Michelle. So I talked about the ultrasound. I talked about that. The health ranger. Yeah, I mean, it's the thing du jour. If you listen to Huberman, he demonizes curcumin as not a miracle antioxidant. He doesn't say it's bad, but it definitely didn't work for him. And he went into a long or short dissertation on curcumin. It's never one thing. What does curcumin do? It's an electron donor. Good. What's its electromotive potential? Maybe it'll work sometime, maybe it won't. So if you understand these foundational things, then maybe you can understand why it may work sometimes and not in others. Let's see. More, you gave me a long link, but you said Josh Yoder, Dr. Naomi Wolf, Dr. Levy, all brilliant people. I don't know Dr. Wolf. Is Karnak holding a classified document? He took some of them and threw them away. He didn't read them, so they must have been classified. I think they wound up in Joe Biden's garage. I'm not sure. Yes, Ed made it hilarious, and I think Dr. Harshfield contributed something along that line. Here's Tommy, LOL. So from now on, we're going to have Harshfield introduce all these talks that I do with that line. And Docs, you may be interested in the Better Health Guy interview with Stephen Fry, microbes and chronic disease. I mean, obviously that's something that is near and dear. Basically, every microbe has its different electromotive force in terms of stealing electrons from you. And so you have to have a treatment that matches or exceeds the electromotive force of that microbe to affect treatment. Simplistically, it's not the whole thing. Jack Cruz says we need to do redox before we do detox. Do you have a comment on that? Wayne, for you? No, I don't. Okay, maybe I'll make one up. But, what it really means is, why are you detoxing something? I use this analogy. You have a sink with dirty water in it, and you clear the drain out. That's detox. But the spigot is still throwing crappy water in. Do you never do detox? I mean, obviously you should be doing them synchronously. but you have to consider both mechanisms of managing what did we call it there? An imbalance of some type. So we always want to eventually get to the source. Now, in my case with Toxoplasma gondii, I'm not sure I can get to the source, but I can certainly do the detox. Okay, donate electrons, because if Toxoplasma gondii is an electron stealer and I can't get rid of it, then I can donate electrons to that tissue and maybe hold myself in homeostasis. Hopefully that answers your question. Dr. Thomas Cowan referenced the studies that the sodium potassium pump can't possibly account for all the energy we ascribe to. Do you agree? Well, I'd like to see, I'm taking someone else's word for this as well. But at the end of the day, we are warm bodies. It requires energy to run that. How many calories do we require a day? You can easily figure that out. A pound of fat has 2,500 kilocalories. You can figure out what the energy needs are, and it has to go somewhere. So if it's not going to active transport, where's it going? And so, some of these processes release energy, ATP. But we have to push the water uphill and then capture that energy on the way down and use it. Okay, so active transport seems like I think it's pretty easy to measure these things by simulating a phospholipid membranes and see what it takes to create a gradient, how much energy it takes to overcome that gradient. So I don't think it's unreasonable to get fairly, I'm not saying one's right, one's wrong. I'm just saying I don't think it's that complicated. And I'd like to see Thomas Cowan's data. And then if he says that it's 10%, not 33%, whatever, where's the other 90% going? So, and maybe we're talking about the difference that, where one's looking at all the steps necessary to set us up for that active transport process, where someone else is just looking at a slice of it. I don't know. But that's why we have to just not just take one piece of data verbatim and look at all the data to see what's really going on. So you're telling me that IM is the MIT version and then some, thank you, of Dr. Huberman. I like his stuff, and he, but like with Rhonda Patrick, they discussed, I forget the name of the substance, but out of broccoli sprouts, vitamin D, magnesium, and fish oils. That's not a 2-hour discussion, but somehow it was, but it's like, I think you can summarize that more quickly. What tests might you recommend for someone suffering from headaches driven by inflammation? Root canals, Wayne, spirochetes, chlamydia pneumoniae. A headache is a miscommunication or an altered pathway potentially. I really call it an energy crisis. So you have a focal energy crisis if you have migraines and headaches, and it's an electron stealer most likely of some type. I mean, we had a lady that when she was 17, she started taking 4 meds for migraines. I got to work with her when she was 41, me and Dr. Carter. She was loaded with spirochetes, chlamydia pneumoniae. We treated her for that. First time she finally, her stomach, her kidney function was going way down because of all the NSAIDs and other things she was taking for her age. And we showed that just treating, and we only treated her for 3 months. She needed a year of treatment. But just in 3 months, she got off all her migraine meds for the first time in her life, and had relatively free. But whereas every day before that, for like 20 years, she had a migraine and started her morning with extra strength Excedrin. Okay, remember that, Michael?
Mm-hmm. Absolutely.
Can you compare TENS units with the energy devices sold by Dr. Tennant? If Dr. Harshfield was on, we could do that, but
there's no comparison.
Hey, guys, can you hear me?
yes.
Hey, Tom. Okay, so the snow, we've got about 8 inches of snow in Fayetteville, Arkansas. and it just blew up the power. So my Wi-Fi's out, but I can talk to my cell phone and chew bubble gum. So sorry about that.
Go for it, David.
Okay. The idea behind what Dr. Tennant's doing is basically repolarizing the spent battery packs. We have about 6 of these little energy fields in our body. They're like little stacked up batteries. And when they are depleted, they flip their positive and negative pulse. And so he's got a transmodulator that repolarizes things, and then they'll accept an energy. And to your point, he's got a whole list of frequencies for each of the organs. All this stuff's been mapped out, guys, forever. And he uses a broad bandwidth pulsed EMF system so that at some point that energy is going to go through the skin and be maybe changed in frequency, go through some sub-Q fat and whatever. By the time it gets to a certain organ, there will be enough of a broad bandwidth of energy being transmitted. Even if it's degraded somewhat, it's liable to be exactly what the kidney or the adrenal needs. And that's sort of how he does his powering. And to your point, the MENS system is about protein, amino acids, and things like that. And I think that's what they're doing. It's that this is absorbed by the cytosol of mitochondria. There's your energy, little battery in your cells, and that helps your messenger RNA to become active in the cytosol and make proteins. Of course, you got to fold them. It takes all this energy, but this is an external way to do it. It's broad bandwidth. And I think MENS is a very similar aspect to what Dr. Tennant's doing.
Yeah, and I think MEMS, you just don't, it's more targeted and it doesn't penetrate as deeply. That's what Dr. Pollack said. So, at the end of the day, you're getting electrons, but how far, how deep, how much, all that stuff.
One last thing I was going to say, and that's the reason I bothered to get back on and interrupt, but we were using this treatment where for vascular patients, we could revascularize the legs and grow the nerves back, and the reangiogenesis and whatnot, grow arteries. So we could increase flow to the legs and these folks with diabetic ulcers and so forth. The problem was the venous outflow. The heart would pump blood into the foot, but you couldn't get it home because the second heart is your muscles, and these folks had so much pain that they couldn't walk. And if you're not walking, you can't squeeze the blood back to your heart. And we developed kind of a protocol where patients would stand on this vibrating platform. And Michael, I bet you know what this is. And it would vibrate in your legs. All the lymphatic fluid and venous stasis in the lower extremity through this vibration in your feet would go into the vascular system. Okay, now we've got all the toxins circulating, all that. Then the red cells, okay, those little guys are not charged properly, right? They don't have the negative charge, so they're sticking together into these rouleau poker chip stacks, and they can't carry oxygen efficiently. So after the vibration, we'd put them in the pulsed EMF system. And TJ Williams is really good friends with William Pollack and taught me all this stuff. So we'd recharge all the stuff that's in the body, but particularly the red cells. They get away from each other so that they could carry oxygen more efficiently. Then we put them in a hyperbaric oxygen environment, and that would oxygenate everything. And then at the end of that, we would take it back and do a vibrational thing to remove all those fluids again out of the lower extremities. It worked great. And it's exactly, I think, Thomas, what you're talking about tonight. How do we get electrons where they belong? And some of it's mechanical vibration, and others chemical, and then others is like infrared and pulse EMF and those sorts of electrical sources. But any and all of those things are important.
So I think, David, too, the point we have to I want to remind people of is that electrons heal, yet your immune system uses an anti-electron, an oxidative process. But see, infections don't necessarily have, if you kill it, it doesn't have this complex physiology to repair. So when we do oxidative things, yeah, we can create oxidative damage. Okay, but we have repair facilities. So we can recover from, the ozone therapy or other oxidative therapies. Can they be harmful? Maybe short term, maybe more so if you don't have good repair pathways. But the pathogen doesn't have that repair pathway, so we can take advantage of that to do destruction. And of course, antibodies, white blood cells, they do that very specifically, whereas ozone might be more general when we say, uh-oh. But once again, electromotive potential, what tissue is it damaging, or is the electromotive potential of the tissue above or below that of the infection and that of the reactive oxygen species, and that would dictate whether there's damage or not, but we will repair. That's why I always tell people, Huberman also talked about adrenaline imprinting. He's a smart guy. And, my adrenaline imprint moment for today before Dr. Harshfield lands the plane is if you look in the toilet when you poop and it's brown, you're healing. You're repairing because you're replacing all your red blood cells every 4 months. And a red blood cell that's been de-ironed by your kidney winds up in the toilet as brown. Okay, so praise God that you see the brown poop. It means we have healing and recovery pathways. And the infectious species does not. And with that adrenaline imprint moment, David, you want to land the bus? You want to land the plane?
Well, maybe the bus.
Land the bus. What the heck?
In the
It's safer on a bus, according to Josh Yoder.
Absolutely.
Potentially.
Well, it's getting that way.
Yeah.
I think again, Thomas, thanks for the series of talks here and tying this all together. And we're not applauding and laughing because this is the end of it, like they did with Karnak, the Magnificent. And like Elon Musk said, sometimes the answer is not the hard part. It's asking the best questions. There's a book that Elon Musk loved, and it's about something about the universe, for just how to search the universe. It's kind of a comedy, but the answer to what is the universe is 42. The answer is not important.
Exactly.
The questions, we got to keep asking great questions, Dr. Lewis, and you do that.
David, you did a fantastic job circling back to Karnak. Amazing. Thank you very much for that.
Okay, and thank you, Thomas, and Michael, and the whole crowd of our community scientists. Let's all have a good week.
All right.
The dream team.
Bye now.
Thank you, gentlemen.
Thank you.